All right. So you might be wondering, because we haven't finished the other set of notes, like, what is this?
Wait, this is more notes?
Yes.
What?
So here's the thing. They're a little bit different. They look more like, they're just kind of like the PowerPoint print off. And the reason that I have this separate is because this packet is entirely about graphs. All right, so motion graphs. If you recall, you have two of your vocab terms. One is position versus time graphs, and one are velocity versus time graphs. And so that's what we're going to spend the rest of this week on, is looking at this graphing stuff. You already have a little bit of an idea of what this is all about because we talked about graphing with density, and we were using those variables, and we're going to use those same variables. Nevaeh, work on it on your own time. This is my time.
Yeah.
Thank you.
Her time.
I'm glad that you're excited to do it, but just stay with us. And so this used to kind of be included in the notes, and like it just got a little long and a little bit more confusing. So I just separated it out, and it has worked well the last 5 or 6 years doing it this way. So it's weird that we have two sets of notes for this same unit. I made these ones white so that I could say, hey, get your white graphing notes out, and it's just a little bit different, obviously. They look different, they're set up different. The screen, like the slides are gonna go like slide 1, slide 2, drop down for slide 3, then slide 4. So you're kind of going that way as you're following along. There are just a few blanks that you're gonna be filling in. I know there's not a lot of room, so I didn't have you fill in a lot of stuff. But when we start to graph, I think there's more of this tomorrow, but when we start to prove that the lines do what we say they do, you're gonna need to be graphing on your little graph what I'm graphing up here. So just be aware of that. I don't think we do any of that today, but just kind of wanted to make sure I tell you that. So this is all the graphing information. And so then if you need to find out about graphing, like you have a graph question, well, you just go to this packet, right? You don't have to look in the other set of notes. And there'll be lots of examples and things in here. So slide number 1, motion graphs are definitely an important tool. Hey, stop it. That shows the relationship between position, velocity, acceleration, and time. Right? Position is just our generic for distance or displacement, right? If you're saying like, what is the current position? Are you looking at, that could be representing displacement, or that could be representing distance as well. All right, and so we're gonna be looking at two types of motion graphs. The first one is a position versus time graph. Notice that they show velocity. The second type is a velocity versus time graph, and they're actually gonna show acceleration. And so a lot of times people want to say that the velocity graph will show velocity, and it doesn't. You have to look at the variables. Obviously, we haven't talked about, acceleration yet. And so this one will make more sense once we get to that information. But we have talked about distance divided by time and displacement divided by time. Those are the two equations that we've been using for the last week. You guys did a great job on the assignment yesterday. Those are entered in gradebook, and I'll get them returned to you. I have about 10 people that still need to do it, so I'm going to hold on to those until I get them all. But we have a really good understanding of those equations and those variables. And so in a position versus time graph, we know that position is just the generic term for distance or displacement. And these graphs are going to show us velocity, just like a mass versus volume graph showed us density, okay? And so if the variables match up with the axes on a graph, that information on the equation and on the graph are going to be the same. And so this is one of, we have this word instantaneous. When you think of instantaneous, what does that mean? What does that make you think of?
Immediately.
Like right now, right? Good. And so it can also show us the instantaneous position of an object. So this is going to kind of show us the motion that an object is going through. And as it's going along its pathway or whatever, you can pick an exact spot and know right where that object is. Okay, we call that instantaneous position. We can also determine where an object started. So its starting position based on the y-intercept point. And this is actually just a little bit more confusing. Like as we get into it, you're like, oh, okay, that's all that means. It'll make sense. I promise. So remember the parts of a graph. We have our x-axis, which is our horizontal. It is also what we call our independent variable. We have our y-axis. It is our vertical. It's our dependent variable. So what happens along the x-axis causes the effect we see on the y-axis. And we have to have correct labels on all of those units. So basically it's like a little description for what's happening on each axis. And if possible, we need to include units with that as well. Right, so our independent variable will be down here, dependent is up here. Now, when I mean label the axis, I don't mean you put independent variable. I mean you put, like we did with density, like this would be our milliliters, our volume in milliliters, or our volume in centimeters cubed, right? And then over here we had mass in grams or mass in kilograms possibly, right? So that's what I mean by a label. All right, so here's the labels. We have time, and then the units are seconds. Here we have position, and the units are the meter. Has a nice little title. And so something that's kind of nice with these graphs, the labels and the axes are always set. Like we always know, for this to be a position versus time graph, this has to be time, and this has to be position. Kind of easy because it matches the title, a position versus time graph, right? The title matches what those two axis labels represent, right? And so remember, position is just our distance or displacement. Nothing too shockingly new, right? You guys with me?
Nope.
Good. All right, and so the position of an object is always going to depend on the amount of time that's gone by, which is why this is the independent variable. So as time kind of clicks by, it's going to have an effect on your position. So think of like you going on a road trip. As you pull out of your driveway, the time starts, right? You're 1 minute away, 2 minutes away, 3 minutes, 5 hours, 10 hours, whatever. As you move, as time goes by, your position changes, right? And so this is our independent variable, this is our dependent. All right, and so lines have a slope, right? Even a curved line, if you find the slope at different spots along that line, have a specific slope, right? And so we're going to be able to use the slope to help us, just like we did with density, where we might not always have to calculate the speed or the velocity. We can just use the lines and interpret them and not have to like do an actual calculation. All right, so the slope is going to indicate the velocity. Now, if this position is dealing with distance, then this whole thing is showing a speed instead of velocity. If it's displacement, then this line is showing us velocity. And so, that was one of the questions yesterday. It said, how can you make speed a velocity, or vice versa? And it's just whatever your length unit is. Are you using your length variable? Are you using distance? Then that's speed. If you're using displacement, then that's going to be a velocity, right? So the same thing here. If this position's distance, the slope gives us speed. If this position is displacement, it gives us velocity. And that's just matching what we've already talked about. Okay? And so by examining the slope, whether it's straight, whether it's curved, whether it's positive, whether it's negative, that's going to help us determine the speed or the velocity, and a little bit about the motion of the particular object. Okay? We know that slope is rise over run, and our rise is going to be our change in our y coordinates. So if I change from 4 to 10, my change is 6, right? And my change in x coordinates is my, my run, right, my horizontal, right? So it'd be like changing from 2 over here, right? So as you pick these points, oops, there's my point, 2 and 5. And we'll look at a few different ways. I showed you with density what I thought the easiest way to calculate slope is, and you guys did actually pretty good with that. So this is just kind of a refresh of that. But now instead of mass and volume, you have position and time to match the variables of the speed and velocity equations. And remember, the little triangle means change in, so our change in position on our y over our change in position on our x. Okay, so we know that on a position versus time graph, our rise or our change in position over our run is really our change in time. Well, that matches our speed and velocity equations. So really we're getting a change in position over a change in time, which matches our equation, which is why the slope of these graphs show us speed or velocity. And again, we've already introduced this with density, so it's the same process and the same kind of rationale, I guess, that we had before. And so slope equals velocity. Most of the time, we're going to be dealing with velocity. Again, if this position was distance, then we know that that velocity would be swapped out for speed. You guys still with me? Yeah? Okay. Make sure if you're not sure, want something clarified, you ask. Okay, so this one's actually looking at speed because over here for position, it has distance. So I see my distance in kilometers, I see my time in hours. So that's going to be important. Do you remember, do we need to include units if we're talking just slope? Do we need units for slope? Correct, we do not. Nice. It's the only thing that we're going to do where units are not included. And I really don't know the answer of why that is. Slope just, it's not, I guess it's more just looking at like the angle. And so it's not really taking the variables themselves into consideration. Obviously the variables make the slope, but we don't have to include the units with it because we're just looking at that angle. Now, if I would say, what is the speed of this? Well, then you'd have to include the kilometer and the hour. But because if we just are gonna calculate slope, then we don't have to worry about the units. So they have picked 2 points, right? You can pick any 2 points. We said that it's easier when they cross like both the grid lines. Like don't pick a point out here because that's kind of like no man's land. Like this would be good for the time, but it puts you kind of in limbo in between on your y-axis. So they picked here and here, right? And so they have a change in position of 600, right? They went from 1200 to 600, and they went from 3 to 6. So really you're getting a change of 3 hours on your run, right? 6 minus 3, and you're getting a change of 1200 minus 600, or a change of 600 kilometers total. So you're going to get a slope of 600 kilometers divided by 3 hours, and your speed is going to be 200 kilometers per hour. So you can calculate the speed from the data in the graph by using the slope. If I had just said, what is the slope of this line? Then it would just be 200. You don't need that kilometer per hour. Yes, you guys are being awfully quiet, which is a little scary sometimes. Good. Okay. All right, now the thing that's nice about this is that you don't always have to actually calculate the slope. Sometimes you can just use it as general information. So The slope tells the story of the motion. So it's gonna show a few things. It's gonna show how fast it moves. And so obviously the steeper the slope, the faster. And we will prove this tomorrow, I believe. And then it's also showing what direction it's moving. So that's why most of the time these are showing velocities, not speed, because that direction is kind of included. Okay. The other thing is that it shows is the motion speeding up? Is it slowing down? Like what's happening to it? Is it constant or is it changing? So constant obviously is going to be kind of like cruise control, right? Changing would mean you're speeding up or slowing down. Right? So I can get all of this information just by looking at a line on the graph. And that's nice. I mean, that's a lot. All right, so here's some examples. So again, I have distance and time. So really this is showing me speed. And so here is a fast, steady speed. And I know that because it is steep and it is a constant straight line, right? That straight line tells me constant or steady, and it's steep, so that means it's fast. This part of the red line is also steady because it is a straight line, no curves, but it's not as fast as my green line. So if you just focus on the red and the green line, the green is steeper, meaning it's going to be faster. Right? Now, blue, it says it's getting faster. Getting faster can be interpreted as a changing speed. It's speeding up. And so that curved line, you're going to have to associate that with changing speed or velocity. Right? Now, this is showing downward, right? It's pointing down. But it is straight, so it's going to be constant, but it is going to be a negative, meaning that it's slowing down. The one that we haven't talked about is this one right here. This is considered stationary. And you're like, well, it's like, it looks like it's moving. Here's sometimes what people want to do with these graphs. Dane and Brooks, make sure you're looking up here. So they want to think like, okay, it's like showing a ball rolling uphill, rolling along a flat surface, and then rolling downhill. That's not exactly what's going on. You have to think of it in terms of, okay, as time's going by, I'm moving away from my origin or the y-axis. And then for a period of time is going by, but my distance away from my origin is not changing. So it's like stopped. And then it turns around and goes back to the origin, is what this is really showing, right? And so anytime you see this flat line, I think about like a heart monitor, like an EKG. What happens if an EKG monitor has a flat horizontal line like that?
They're dead.
No heartbeat, right? Can somebody move positions out of that bed if they are dead?
No.
That's how I remember it. Like if it's showing a flat line on a position versus time graph, there is no motion. Okay, a little bit morbid, sorry for the sad example, but it's kind of fitting, right? Now here's the other thing. What slope does a perfectly horizontal line have? Zero, right? Now, a vertical line, anybody remember what that slope is called? Undefined, right? Because you end up with a zero as your run, and so you have a number over zero, right? And that fraction is not possible, right? You can't have zero as your, hey, stop, thank you. You can't have zero as your denominator, your bottom number, right? And so we will kind of prove this as we get to some more examples, I think, tomorrow. But this one is actually just zero because your top number, your numerator, is zero because you have zero vertical change, but you still have a denominator. You still have a bottom number. You might have, zero over, this might be 3, 0 over 4, 0 over 5, 0 over 6, right? But that's okay. That just makes your slope 0. But if you have 0 as your bottom number, your run, that's undefined, okay? So the math proves that this would be 0, but really you don't ever need to even try to calculate the slope of this line. It's just like a flat line on a heart monitor, right? It's gone. No movement necessary or possible, because they're dead, unfortunately. Okay, so if you see these two cars, you see like this car is traveling, it looks like, and we don't have really units on here, but here it's meter per second, so it's 70 meters per second. The red car is traveling at 100 meters per second. And so obviously you can see that the red line is steeper, meaning that it is traveling faster. Obviously, logically, 100 meters per second is faster than 70 meters per second. And so you could calculate the speed or the slope, but just looking at it, you can interpret that, and that's nice. You don't have to always do a calculation to figure out the slope or to figure out using the equation. You can just look at it and be like, okay, which one's steeper? That's the faster one. Okay. And so that's kind of nice. Same thing that we had with density. Whichever line was steeper, right, that's going to be the more dense. And so the same thing applies here. But instead of density, we're talking speed or velocity. Now, this is a really important slide, and we're going to prove this is true tomorrow, but these are the main things. So if I show you these graphs, you should be able, by the end of this week, you should have a real good understanding of being able to put all this together. So if I look at this, I should be able to tell that I see straight lines. That's going to be showing me constant motion, right? So these two are both showing me constant. These two are both showing me a changing motion. And the reason it's changing is because the slope is different. It's different here, 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 and here. Same thing here. You go different, 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 different as you go from those different segments of that curved line, right? And so straight line always means constant motion. Curved always mean changing. So that's one thing I could ask, which one is showing constant motion? Now constant is like cruise control, right? So if a vehicle is traveling at, 2 meters per second, and then 3 meters per second, and then 4 meters per second, that would be something that's changing. But if it's just traveling at 2 meters per second the entire time, that's like cruise control. All right, so this one is going to show us constant, and it's also positive. We haven't talked about acceleration yet, but this is actually showing 0 acceleration, because if you are on cruise control, you're not speeding up or slowing down, and that's what acceleration is. Our next one is we have an increasing, which we know it's meaning changing, but in the positive direction. So it's speeding up as we go up and to the right. Over here, we have a constant negative velocity. And I know it's constant because the line is straight. I know it's negative because it is going down. And when you calculate it, the slope would actually be negative, right? So this is like something that's moving backwards or possibly like returning to the origin. And then this is considered decreasing, which is a change. So it's matching our changing motion. But I know it's going down because the slope is steeper here, and then it gets less and less and less until it's almost horizontal. So it's almost to 0, right? So this is slowing down, this is speeding up. Both of those are considered changing motions, obviously. And so they do have acceleration. And those are going to be some of the main things that we'll look at. Okay, so we're going to prove that what I just told you is true. So it's nice not to just have to take my word for it, that, I can prove with math that this is actually taking place and it's like legit. All right, so remember what I do, I know that your little squares are small, but try to follow along and do what I'm doing. So we're gonna use math to prove it. So we're gonna find the slope at two different places on the line, and they should be equal, because this is a straight line. And so if this is a straight line, then the slope at any location should be the exact same. So this slope here, 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 should all be exactly the same, all right? So we're gonna pick 2 points where it crosses our grid lines. So we don't have to pick the plots. These were like data points, all right? We don't have to use those data points. We're gonna pick points where it crosses the grid. So it has to cross, horizontally and vertically. So let's just start here. And it looks like the next time it crosses both is right here. Let's use this as our first slope, okay? So we're gonna go, and I said that the easiest way that I think is making sure you know what each space is worth. And this is worth 5, 10, 15 as we go vertically. But each space is not worth 1 down here. We have 1, and then we skip, and then we go to 2, skip, 3, skip. So really, what is each space worth on our x-axis? Brookston?
Half.
Looks like half, and let's try it.
Well,
This is also weird because, like,
No, it's not. It goes from
Yeah.
0 to 1.5. Doesn't go.
So, the reason they started it here is because that was their first data point, and it matched 1. So they could have added an additional space to make it half, 1, but they didn't do that. So that's good to notice, and you probably are kind of like, wait, that seems kind of weird. And it is a little bit, but it just matched their data, and that's what they went with, so it works. So let's check to make sure. If this is 1/2, 2.5, 3.5, yep, it's matching. So each space on the X is worth half. So if I go up 1 space, that's really a vertical change of 5, right? Because 1 space was worth 5 meters. And then it went over, and we're gonna go 1/2, 1, 1.5, 2, 2.5. It changed horizontally 2.5. And so when we take 5 divided by 2.5, we end up with 2. Right? So that's the slope right here. And so remember, this is what I think is the easiest way to do slope. If you have another way that you're comfortable with, if you like to do the 5 minus 0 and then the 3.5 minus 1, you can do it however you want. If you want to do that extended version, but I think it's easier just to count up the change, which is 5, and count over the change, which is 2.5, and do it that way. So let's pick 2 more points. Here's one where it crosses both, and this looks like another. So we don't really have too many options, so same thing, we're gonna go up 1, which is really a change of 5 meters, and we're gonna go over from that point 1/2, 1, 1.5, 2, 2.5, another change of 2.5, and so our slope is 2. It is 2 here, it is 2 here, proving that a straight line gives you a constant velocity or speed. Good? Yes? Now, if I wanted to find out what the speed was, I would have to include the meter per second on these. But if it's slope, then I can just leave it as 2. All right, let's go to number 16, and we're going to prove that a changing slope is a curved line. So proving that a curved line is changing. So let's go. It looks like it crosses here and here. Okay, and so that is going to be basically 8 minus 16, right? 8 and 16. And so my change is gonna be -8. My time, right, so as I drop down, I go a difference of 8, and as I go over, I have, each space is still worth half, 1, 1.5, 2. I have a change of 2. And so this is a slope of -4 for this first section. All right, now I'm gonna go across here and here. So here I'm going, right, I went, over here. I went a change of 4 and 2, right, a change of -2. And then I went over, I went from 3 to 3.5 to 4, so a change of 1. And so that change of slope is -2. So this was -4, and this was -2. Those are definitely different. 4 is not 2. If the subtraction part giving you negative confuses you, all you have to do is think if it's going down, it's gonna be negative, okay? And for us, that's really all we need to know. So we have these two proving that a curved line has a different slope, right? And then the straight line had a constant slope. Still good with that? Good. And really, I mean, this isn't too difficult, I don't think. We're gonna go ahead and we will stop there.